Okay, so we are having this question before us about how we can tell the difference between these two molecules in mass spectrometry. Yes, they have the same mass. That's why we're trying to think of other ways to tell the difference. And there are many ways. And I asked you to think of 3. So let's take a closer look at these molecules again. CH3Cl. So once again, it has a mass of 50. C4H2 also has a mass of 50. So all that means in terms of its mass spec, remember we have a percent abundance and we have mass to charge ratio here, is that the M plus peak would be the same. They'd be around 50. Everything else about the mass spec, there's no reason for it to necessarily be the same unless it's a coincidence. In fact, it's a coincidence that they have the same mass, right? It's like I picked them because they do. But that's the only thing. If we only had the M plus value, then yeah, we don't know what's going on. But if we had the entire mass spec, which would include, remember when we look at mass specs, we have kind of 2 regions that we really hone in on and focus. So we have the whole M plus region, and then we have the everything below it, which is where all the fragmentation happens. So even right below it. So here's where, here's where we look for all the, anything less than the M plus means that it's smaller than what the molecule started off with. So we look for fragmentation patterns here. Here we look for the molar mass if we're lucky enough to see it. But then in this region of the M plus, anything bigger, we look for M plus 1, M plus 2, etc. And that gives us information about isotopes. So, and we could even get the formula if we have high enough resolution there. So that gives us information about certain atoms that might be present. So remember those isotope distributions. So isotope distribution. So use that percent value. So keeping that in mind, we should expect to find some information in the yellow region and the green region that differs. The only thing that stays the same is the M plus value. So of course, they're different molecules. They're going to fragment differently. So different fragmentation patterns. Yeah, so in other words, the peaks in the green region wouldn't look the same. What makes a good carbocation for one wouldn't make necessarily a good carbocation for the other. So in other words, they'd probably have different base peaks. So that kind of falls under that category. For example, different base peaks. Tallest peak, right? Number 2, what about the yellow region? So that took care of the green region. That was a generic statement about the green region. We kind of labeled that there already. Is their M plus 1 going to be the same? Well, do they have the same number of carbons? One has 1 carbon, one has 4 carbons. We know that M plus 1 is thanks to carbon. So get the number of carbons. That's relating directly there. So they would have a different M plus 1 values. So what would those be? So M plus 1 for CH3Cl versus C4H2. So the M plus 1 value for CH3Cl would be 1.1% because there's only 1 carbon. But since there's 4, it'd be 4 times that, 4.4%. So they would not be equal. So we're going to kind of highlight these differences here. Now, M plus 2 could play a role if you have any of the atoms in the formula that give you information about M plus 2. So the one with only C's and H's, C4H2, would not have anything to show in the M plus 2 peak. However, remember, chlorine has a very significant M plus 2 peak. So the M plus 2 for CH3Cl, the one with chlorine, would be about 33%, 1/3 of the M plus peak that it had. remember it had the 3-to-1 ratio, so that would be its M plus, and about a third of that height would be the M plus 2. And then of course we'd have the M plus 1 in there. So that's a dead giveaway that chlorine's present, so it would look different, right? So those are 3 ways that even if the mass is the same, that you get other information from mass spec that's very useful. Now, we have talked about, we're going to expand on number 2 and 3 for a minute. We've talked about what goes on here. This helps put the structure together. In this region, this could actually give us specific numbers of atoms present. And so we're going to expand on this idea and try to actually pull out, if that data is provided, pull out the information that will lead us to potential molecular formulas. So it's very useful. So here are some tips and steps to take for when you are presented with that mass spec data with all the percentages for M plus 1, M plus 2, etc. Then you take these steps to try to get the molecular formula. And that will be a big step in solving the final structure. Okay, so a few things to bring up. Here's our checklist as we go through, or just some pointers. You don't need to worry about any other elements present other than our Fonkel-Berish group. So don't try to fit zinc in there or anything else like that. Furthermore, just don't worry about F or I being present in the mass spec. They're a little harder to detect by mass spec. So, and other spectroscopic techniques as well that we are using in this course. So if they happen to be part of your formula, you will just be told, okay? Because you have to use other techniques to confirm their presence. So in other words, it's going to be mostly Onkel Birch. So now that simplifies that even a little bit more, right? Then what do? You should always start with M. That's your molar mass, okay? So you're going to get your molecular weight. It will have some percent abundance assigned to it. Now, the base peak by default gets 100%. In order to get a ratio and a relationship that'll work in the M plus region to find out the formula, you need to scale everything so that your M plus has 100%. And it usually won't have one. Sometimes it will. If not, find out what you need to multiply it by to get it to 100%, and then you multiply everything by that so that the ratio stays intact. This will make your math a lot easier. So in other words, your M plus, whatever that is, if it's that, turn it into 100%. Once you've done that, that's all you do with M plus. So you systematically treat each region of that M plus region, that yellow region I talked about over here. That yellow region. So you start with your M plus, you make that 100%. Then you move on to M plus 1. You divide that by 1.1, the abundance of carbon, 13, and that gives you the number of carbon. Very useful. Then you go to M plus 2 and you look for the characteristic M plus 2 culprits, sulfur, chlorine, bromine. And you could tell which one is which by their ratio, their relationship to M plus. Okay. After that, those are your for sure items. They're in your formula. You will add all of those masses up, and if you equal your total mass, you're done. But most likely you didn't because you have to account for hydrogens. So anything left over will be given to oxygen, nitrogen, hydrogen, and we will vary that until we get a reasonable formula. Don't forget your friend, the nitrogen rule. Okay. In fact, I like to add that tip up here again because it's easy to forget, but also ask yourself about the nitrogen rule with your M plus. See if that applies. Do you have an odd mass or an even mass? Okay, you ready for an example? One more tip that seems straightforward, but it's a good reminder. Rule out formulas that don't match your other data. So you're going to have reasonable formulas given the mass spec data, but most of your problems will be combined spectroscopy problems. So in other words, you might have also gotten an IR or an NMR, right? You might have calculated the DUN, and in fact, we'll be doing a lot of that again. So When you do that, rule out anything that doesn't match. Like if your IR shows clearly there's an OH, then you can look for the formulas that make sure they have an O in them, right? You can rule out the ones that have no O. So we'll do that in this problem. Okay, here comes a problem. Let's prepare for it. Look at what you are given. You are clearly, that you can see the IR kind of staring at you, so that's kind of your extra piece of spectroscopic data, but the goal of this topic is to focus on how we're going to use mass spec to help us get the formula. So notice what it's asking: determine all reasonable molecular formulas and calculate DUN given the following data. So you don't see a picture of the mass spectrum, so notice that. You're only given this data. And what does this mean? M, 50%, 173, comma, M over Z. So remember, that's the x-axis, M over Z, okay? So just to remind you you don't have to sketch a mass spec from this every time, but just so you know where these numbers are coming from. Remember, the y-axis is percent abundance, percent. So those percents are from the y-axis values. The M over Z is from the x-axis value. So if we're given the mass spec zoomed in on this region, M basically means M plus, right? Sometimes it's spread as M, and other times you'll see it as M plus. Now, if we're given the M, I'll call it M plus, it's 173. Then we remember that has to be scaled from our checklist, right, to 100%, and it's not. So that means the percent abundance was actually 50%. But we're going to scale it to be 100%. What did we have to do? We had to multiply by 2. Okay, so we will do that to all of them, times 2. Now, what is the next number we're given? M over Z equals 174. Notice that we had 173. 174 is one more. 174 is, in other words, one more than M plus, which is M plus 1. So you're given M plus. This is M plus 1. Sometimes that's actually spelled out for you, and other times it's kind of obvious because it's the mass, right? 173, one more than that is 174, so that's M plus 1. Other times, so most of the time it's not labeled though, so be ready to interpret that. And then 175, well, compare that to M plus. How much more of it is it? 173 to 175, so that's M plus 2. Okay, once we scaled this one to the M plus to 100%, we have to scale all of these to 100%. And so to be prepared for this kind of problem, you want to have a little calculator probably, because sometimes they're, the math's very easy, honestly, but it's sometimes decimals, like 4.7. So 4.7, if we scale that to 2, you should get 9.4%. Scale it by a factor of 2. And then we multiply 17% by 2, we should get 34%. Okay, so we did this. If you look at the checklist, we looked at M, we scaled everything to 100%. We're not done with M. Okay, so once we have M, I'm going to highlight M right now. Here's my M value. So we scaled it to 100%, so that part's done. What else do we need to do with M? We're going to look for the nitrogen rule. How do we apply the nitrogen rule to M? So let's see. M is 173. 173 is an odd number. Therefore, we have an odd number of nitrogens. Therefore, we do contain nitrogen. We have 1 or 3 or 5 nitrogens, okay? That's already a revelation as to part of our formula. We know we're going to have a nitrogen in there. So don't forget that. Now we're done with M. That's what we get out of M. We make sure it's 100% and we find how we can apply the nitrogen rule, what consequence that has on our formula. Okay, now I'm going to look at the next one? M plus 1. There's M plus 1. That's percent. It's 4.7, which is now 9.4. M plus 1, we're supposed to get the number of carbons from that. So remember, to get the number of carbons, you might be referring to this very frequently. So that's in your course guide. Remember that for carbon, if this is the M plus column, this is the M plus 1, and it's the most significant, which is where we get the 1.1% from. So we're going to use that and divide 4.7. Actually, no, we multiplied it. So that's our new number. So we're going to make sure we pay attention to that one. Divide 9.4 by 1.1. And what number does that give us? So if you plug that in a calculator, you're going to get 8.5. So I'm doing this problem on purpose because that's the most annoying number you can get for M plus 1. It means we are right in the middle. We have 8 or 9 carbons. But hey, we had no information until now, so I'll take it, right? So that's another, let's circle our important things that we don't want to forget to help us get our formula. Okay, finally, the last section, M plus 2. So that's all you get from M plus 1 is the number of carbons. M plus 2. M plus 2 is 34%. When is that significant? Remember, M plus 2 is the only thing we use M plus 2 for is to look for chlorine, bromine, or sulfur. How so? Look at those ratios, the percent. So this percent's not fixed, it's the ratio that matters. So notice that if chlorine, notice these aren't 100%, but if they were scaled to 100%, then we would compare it to the other one. So chlorine is present in 75% is 35, but only 25% is 37, so that's a 3-to-1 ratio. Or in other words, this is 1/3 of that. This is 50-50. These are a 1-to-1 ratio. And this is 4%, so it's small but big enough to be seen. So which pattern does this represent the most? 3-to-1, 1-to-1, or 4%? So think about that. Let's take a look. Remember to look at this number, our new number, our scaled number. 34% of 100 is a third. So we have a 3-to-1 ratio. It's a third. So if I were to draw this out, like a third of it, right? So a 3-to-1 ratio means we have chlorine. Wow, so that's a lot of good, useful information. We know we have a hydrocarbon that contains nitrogen, chlorine, and 8 or 9 carbons. From there, we have to use what else we're given. So we are given IR, and that's it. Sometimes we're given more. This time we're only given IR. And notice that it's not asking you to come up with a structure, because it's hard to get a structure with mass spec alone. The goal of mass spec is often just to get to the formula. We could possibly get closer to a structure if we had the fragmentation or the whole mass spec, but notice we were only given information in the M plus region, so the M plus and higher. Below M, there was no information about fragmentation. So that's this one style of problem you'll see quite frequently, is that it's focused on the M plus region, or it's focused on the whole thing, maybe even just with an emphasis on fragmentation. So there's no fragmentation in this problem. We'll do that in another example. This one's focusing on how you use the M plus region when you have that much detail. And don't worry, this problem will keep us busy enough, so it'll be good that we treat them separately. Now, I'm going to move this back up. This is our reference. I'm going to pull down the other thing from that same data sheet. We want to not forget some peaks that might be helpful. Remember, we're looking for CN groups and CCl. And CCl is not on there. It doesn't give a very significant IR absorption. But CN, what kinds of CN groups should we look for? Amide or amine, NH, So that's kind of a broad, a little bit, I mean, possibly, but that's a little hard to believe. Usually it's kind of narrower than an OH stretch usually, but still pretty significant. In other words, kind of similar to an OH stretch. Nitrile is a sharp, with variable intensity, 2200, a lot like the alkynes. That triple bond region is that sharp peak at 2200. Any other ends? That's it. Okay, so let's see. So I don't think we have an amine, but I'm not going to say it's impossible. Let's look at what else we have. The nitrile would be 2200. So here's 2000. Yep, there. Oh, look at that. That's most likely the nitrile. It's possible that it's also a C, triple bond C. So we can't say conclusively it's one or the other, but I'm guessing because we have a nitrogen and we have to account for that stretch somehow, and we do not appear to have an amine, then it's probably in the form of a nitrile. Here's our 3000 line. We have no sp2s, but we have sp3CHs. So we're working with a formula that has, and I'm not going to bother with anything below 1500 until I know more about what's there. We're working, so in other words, we're going to work with a formula that is C, X, H, Y, N odd, we know it's an odd number, Cl. We have to find those numbers, but that's a good start. That's where we're at. From here, we're going to be kind of systematic about it. And it gets to be kind of fun. It's a little mystery that we're solving, and I'm going to move that up out of the way. So let's dive in. How are we going to do this as systematically as possible? I recommend being as organized as possible and systematic. Maybe even make a table. This is the table I like to make. I know we have this scenario. It's not simply X as anything, it's 8 or 9. So we have to try those two scenarios. So first I'm going to try a table where I have 8 carbons. And then I will do another table with 9 carbons. This is more work simply because we had 8.5. So most problems will be a little less work than this. So I'm going to try 8 carbons first. All right. So what does that mean? That means I need to figure out what else could be there. And how do I do that? I'm going to take my total mass and remind myself, what exactly does that mean? This sounds simple, but it is easy to kind of miss these links sometimes. It means I have 8 times C plus some number Y times H mass, right? Plus some odd number times N plus Cl. When I add all of that up, that should equal my total mass. Well, I know some of these things, so that can help me kind of fill in the holes. I know my total mass is 173. That's from the mass spec. That was the M plus value. I know that I have 8 times, since I'm solving for 8 right now, I'm letting 8, my two scenarios are 8 carbons or 9 carbons. I'm letting the number of carbons be 8 for this first table that I make. So 8 times 12 plus, we don't know how many H's, so that's something we have to figure out from leftovers. And we'll have to figure out the odd numbers of nitrogen, but we also know what chlorine is. Chlorine, we always use that lower number. For M+, we do not have any of the higher isotopes. We only have the lower isotopes, so 35. Okay, so what that comes down to is I have a minimum, when I plug that all in, 173, and then you kind of isolate everything. So in other words, I'll write it all out now, even though I know we all know algebra. 173 minus 8 times 12. So I'm isolating all my unknowns, right? Minus 1 chlorine times 35. That's going to equal, so I've subtracted those, whatever's left over for N, H, and O is a possible one we always like to consider. So we always think about O as a possibility. The only reason O is less likely is because our IR is not indicating the presence of O. But otherwise, it could actually be in there. And so I'm going to assume or O, that O is still possible. And so remember, we're trying to consider all Fonkel-Berish minus the F and the I. So N is made itself present by the nitrogen rule. O we try to consider, right? And then B, R, C, L show themselves in N+2. And so does sulfur. And so C and H. So we have to assume any of those could be present. And so we've already addressed all of them except O. So I'm going to modify my formula to also say an O. We're going to try to see if it's reasonable to consider that O would be there. All right, so let's start this table. Here we go. If I let myself have oxygen, I'm like a table for each unknown. I don't know how many nitrogens I have. I don't know how many H's I have. I'm going to write what my resulting formula would be as I vary these. And I'm going to write some comments on this. Just to, as to whether it's reasonable or not. Some notes, in other words. And so if you organize this like a data table, then you could make sure you don't overlook something that might be important or skip steps. So let's try 0 oxygens. We know we have to have at least 1 nitrogen. So let's try that to keep it as simple as possible. Then, a simple rule of algebra, we can only have one unknown at a time for one equation, right? So we'll let H be the unknown, and we'll solve for how many H's there would be. So how many left over when you plug all of this into the calculator? 173 minus 8 times 12 minus 1 times 35 gives us a number, 42. All right, so 42 is where we start. Notice that we have a nitrogen. Nitrogen has a mass of 14. So we let ourselves have a nitrogen. That means once we take 42 left over for N, H, and O, well, we've said, okay, there's going to be 0 O. There's going to be 1 N. So then we have to take away 0 for the O, so I'm not writing that, minus 1 of the N's. Anything left over from that is going to be whatever we have for H. And H weighs 1, which is why it's nice to do that last. Equals 28. So that means we have 28 H's. So our resulting formula would therefore be C8, H28, ClN. We are going to do our DUN here every time because that helps us decide if it's reasonable. Remember how to do DUN? Okay, so here's the formula in case you forgot. DUN. Remember, it's based on how saturated your hydrocarbon is, so it's derived from 2n+2, plus you account for everything, the way the other atoms bonded to contribute to whether it takes away or adds hydrogen counts to it. So it's also sometimes called the index of hydrogen deficiency, IHD, so those are interchangeable. So in other words, it's the number of carbons plus the number of nitrogens over 2 minus the number of hydrogens plus halogens over 2 plus 1. We're going to do that over and over again in this comment section, plus write anything else that relates to whether it's a reasonable formula or not. So this formula, 8, plug and chug, plus n over 2, so 1n over 2, minus h plus x over 2. Well, h is 28, 1 chlorine, over 2 is 29 over 2, plus 1. Work that out, you're going to get, so I urge you to plug that in, -5. That's not possible, so this is an unreasonable formula. We are not going to use that formula. We got to keep going, keep trying until we get something more reasonable. So another thing we could do is say, all right, part of the problem, look at this ratio. C8 to H28, that's pretty high. So maybe instead of having so much left over for H's, what if I increase the mass that's subtracted from here so I have less H's? So I'm going to let there be 1 oxygen. I'm going to keep the number of nitrogens at 1 because if I change it, it can't be 0. It could also be 3 though, so I'll try that later if I need to. But I'm going to let there be 1 oxygen. So that would mean the number of H's is 42. That was left over, minus 14, but now this time also minus 16. That gives us a total of 12. That means 12 is our number of H's, so we have C8, our new formula would be C8H12, Cl, N, O. And it doesn't matter what order you write that in, I just kind of put that in. IUPAC would care, but we're not gonna dwell on that. Okay, DUN would be 8 minus, so this is a DUN, minus what? 12, let's see, the N over 2, excuse me, plus N over 2. So 1 over 2 minus 12 plus 1 over 2, right? Plus 1. Plug that in. You're going to get 3. Perfectly reasonable. That's a good one. Okay? So there we have a possible formula, but we're not going to say we're done because we didn't consider everything else, and some might be more reasonable than others. So what you do is you go until you basically run out of H's. So I could say, how about, I know I have odd ends, but why not try 3? Well, what happens when you try 3? 14 times 3 has to be subtracted from 42. So 14 times 3, what is that? 14 times 3 happens to be 42. So that's 0. That means we don't have enough for any oxygen, and we also have no hydrogens. Our formula would be C8, Cl, N3, and that is completely unreasonable because we know we have CHs. I'm not even going to bother to do the DUN. So see why that kind of helps to have evaluated the IR. You might be tired of calculating DUNs by now. So I'm going to put a red X and say need CH. It's in the IR. We had a CH stretch. Okay, and the DUN would be pretty crazy. Just in case you're interested, you know, you can actually go calculate it and see that that wouldn't work out so well. So remember, our DUN has to be a whole number. So 0, 1, 2, 3, and it can't be negative. So that concludes our first table. We would normally be done in most problems and just run with the one green check mark we have. But unfortunately, we had the misfortune of getting an 8.5 value for a number of carbons, which means we're not done. We've got to try the 9 carbon scenario. 9 carbons means that we got to do this again, the same exact logic with 9 carbons. But I have a different amount left over, right? Because what does that mean? I have to set up my leftover amount to work with. 173 is going to equal 9 times 12 instead of 8 times 12 this time, plus however many H's I need to find out, plus odd N, plus 35. Okay, I won't draw out this algebra for you, but that gives me a different number left over. That gives me 30 left over for N, H, and O. So needless to say, this calculation goes a lot faster because there's less left over. So that part's kind of nice. So let's do that table now. Oxygen versus nitrogen versus H. I like to give a little bit bigger column for H because that's where I do that subtraction to see how many H's I'm allowed to have. The resulting formula from those calculations, and then my comments to see if that's reasonable, and your comments. Okay, let's get a couple entries at least ready. Okay, we're always going to start with at least one N because we know that that's odd. Let's try working from the bottom and increasing other atoms as we go. 1N, no oxygen, means we have 30 minus 14. Well, 30 minus 14 equals 16. Well, guess what? Oxygen equals 16, so we can never add an oxygen. Well, then we'll have no H's. So we're done with that entry. We're not going to do any more entries. So you get that logic, right? So C9, that means H is now 16, no oxygens, N is 1, and Cl. We will never have an oxygen because if we do, we'll have no hydrogens. So I don't need to belabor that and add a bunch more for no reason. Let's make sure it's a reasonable DUN. I urge you to calculate that and check your answer. I got 2. Good, very reasonable. So now we have 2 winners. Let's compare them. this one, and bring this one down, and this winner. All right, so I'm going to circle them in red too. Oops, I'm going to get my pen. That one versus that one. All right, so who should I put as my final answer? Well, it says, actually, it doesn't say you need only one. It says determine all reasonable molecular formula. So those are the two reasonable ones. There's actually two answers here. So those are both reasonable. The others are not. So my answer would be C8H12 ClNO or C9H16 NCl. So that's my final answer. Now I could go back. I always think it's worth going back to revisit the IR and say, does my IR provide any extra information now that I can go back in hindsight and look at it and say, well, my two contending formulas, the only difference between them is the number of carbons. Can't tell that from IR. Can't tell the number of hydrogens from IR, just whether they exist or not. But notice one has an O and one doesn't. The top one has an O. I don't see an OH stretch here. I don't see a ether stretch, and I don't see a carbonyl stretch. So because the IR is not giving me any indication that an O is present, if I had to bet money on it, I would actually definitely go for, if I had to pick which one was more likely, then I would say this one is more likely, because the IR doesn't give any evidence of O being present. If there was an obvious absorption that indicated some sort of carbon-oxygen bond, then I would be more likely to believe it. But it's not a guarantee. Like I said, IR you have to take qualitatively. Okay, so I hope that helps. You are going to do the rest, but feel free to refer back to this as you need to kind of work through the others in that same systematic way. So once again, this is for solving the types of mass spectrometry problems where you're not given all the fragmentation, you're only given the M plus range, or if you are given the fragmentation, that's a different issue. That's a different approach. And so we'll do that in a separate type of problem. So you could have all that information together, but this is how you address the M plus range and get useful information out of it so that you can get your molecular formula. Doesn't mean you'll get the structure without other information, but you do get the formula. Okay, I hope that helps. Have fun doing the rest, and hope to see you soon.